Hello, we're going to look at a force problem with something on an incline. And so let me just kind of sketch out in your lab. You have a problem that asks you to look at a cart that's on an incline. All right, and so one thing that you want to do for each one of these problems is draw a nice picture. So I'm going to draw this one at a 30-degree incline. You might have, I think in the lab you had a 20-degree incline, but this could be any number of inclines. So if you have a incline here, I've made this one 30 degrees. So this is 30 degrees. And then the cart is up here on the incline. We'll just represent it as a box like this. And then we want to draw a free body diagram on the box. All right, and so I'm going to put my force vectors on here. So we have three force vectors that we need to be concerned about. One of them is gravity, and gravity acts straight down. So if I get this lined up, I can mark where straight down is. So that's about straight down. Let me see. Is that about straight down? Right there. So we're going to draw that one straight down. So this is the gravity. So we'll label it W. And then we have the normal force, which is heading, the tension, which is heading parallel to the surface. And then the normal force is perpendicular to the surface. Let me draw it. Okay, and so I've got a nice free body diagram. Notice I'm making a nice large free body diagram. Please use plenty of space, all right, when you're drawing these. All right, so when we're solving these, remember Newton's law is the sum of the forces is equal to mass times acceleration, all right? And so we need, on the left-hand side of this equation, we have to add up all the forces. And on the right-hand side of the equation, we can deal with the acceleration. Okay, so here I've got three forces. I've got the normal force, tension, and weight. And we need to apply a coordinate system to the problem. And the coordinate system that is really helpful is if you let one of the axes align with the direction of motion or the perceived direction of motion. All right? And so the direction of motion would be along the incline. So we can let this be the x direction right here. And then this would be the y direction right here. All right, so we have our x direction and our y direction labeled. If we just turn our page this way, we can see that tension is aligned in the x direction. The normal force is aligned in the y direction, but the weight is not. It's off in this third quadrant, okay? So we have to take the weight and we have to break it into its x and y components. So just for clarity, I'm going to extend my axis, my y-axis this way, and I will extend my x-axis this way. Okay, so now I've got my x and my y-axes labeled and drawn. So this force right here, the weight, I'm going to break it into its component vectors. When I do that, you have to remember that the weight vector is the hypotenuse of the triangle that we're going to draw. All right, this is the hypotenuse. I need to find out what are the two short legs. All right, so do not draw a horizontal line this way. This would have two components and a larger vector. All right, our coordinate system is like this. So I need the weight, which is in the x direction, to be like that. Okay, so I'm going to draw the two components here. So I should have one component in this direction, like this. And then one component in this direction here that aligns with the y-axis. So this is wy, and this is wx. Okay? So now that we've done that, then we can add up the forces in both the x and the y directions. Okay, so while this is a vector sum, let me illustrate that with the vectors here. Right, we're going to break this into two problems just like we do with 2D kinematics. We're going to add up all the forces in the x direction, and we're going to add up all the forces in the y direction. Okay, so in the x direction, I have tension in the positive x direction, and I have Wx in the negative x direction. Okay, and then in the y direction, I've got the normal force in the positive y direction, and I have Wy in the negative y direction. Notice that we're taking care of the directions in these two equations here with signs. Tension is in the positive x direction, so it's plus tension. X part of the weight is in the negative direction, so it's minus Wx. Okay? Same thing here. Normal force is positive in the y direction, minus Wy in the negative y direction. Okay, so now we've got that, we're ready to look at the right-hand side of the equation. So this is equals, all right, the acceleration in the x direction, which if this is in static equilibrium, acceleration is 0. If this is in the y direction is in this direction, so that's also 0. There's no acceleration in either direction for static equilibrium. All right, so at this point, we've got our two the forces in both the x and the y directions. I have to look back at my free body diagram to figure out what the relationship is between Wx and W, and also Wy in W. All right, so if I look at this triangle right here, I need to know this angle right here. What is this angle? Okay, and a little bit of geometric work will tell you that this angle and this angle are the same. This is 30 degrees, that's 30 degrees. But since we made a nice drawing, we can extend this out and measure this angle. Let's measure it. And if I get my protractor on here, I can measure it, and indeed it is 30 degrees. All right, so a nice drawing, again, really helps. Okay, so then when we look at this Wx, we know that it's related to this angle and the hypotenuse based on the sine function. The sine of theta is equal to Wx over W. So Wx is equal to W times the sine of theta. And you can come up with a similar expression for Wy, but it is the cosine of theta. Okay. All right. At this point, we're ready to put these terms in up here. So we're going to plug this in right here. And for this particular problem, we don't need to worry about the y direction because we don't need any information from it. But when I do that, I get t minus W times the sine of theta equals 0. So the tension has to equal W times the sine of theta. All right. Now, the weight, remember, is mg, mass times gravity. So if I put that in, mg sine theta, then I've got my expression for tension. Okay, and so this is how we can solve for tension in this line. Now in the problem, this line right here, in the problem in your lab, you also have a pulley with a mass hanging off of it. So you need to draw a free body diagram here, noting that the tension, which is this tension right here, is the same as this tension. Okay? And so then you can solve for the mass that's required to keep the cart in static equilibrium. All right, so this is how you can solve these types of problems. I will see you on Monday.